late at night for some others. But we're going to get started in a couple minutes. Very good. Very good. Cool. Should we get Daniel? Okay, I suggest we get started. Welcome everybody to ICCRG, the Internet Congestion Control Research Group. Please remember to join MeetEcho either via link from the agenda or by scanning the QR code in the room. I'm Rhys Enghart, co-chair of ICCRG, and we have Vidi with us online. You want to say hello?
Hi everyone, I am remote today. Rhys, thank you for coordinating the session. I'm here. I'm just gonna, see if there are any questions that I need to answer, but I'm here. Thank you.
Awesome, and thank you for being with us, Vidi. Reminder that the session is being recorded. Chances are you've already been to a few of these now, but if you want to speak, please enter the queue in either the on-site tool or remotely. Please keep your video and audio muted until it is your turn to speak. I'm going to call on you. And please state your name before speaking. And if you're remote, use headphones. Thank you. Now, this is an IRTF session, but the IRTF follows the same intellectual property rights as the IETF. So please make sure you're familiar with those rules if you're planning to participate in the discussion. As noted earlier, we are recording this session and we will make the recordings available online. And more generally, please note our privacy policy, which is up on the slide. And then we do also have a code of conduct. Let's all do our part to make sure we're being professional and respectful to each other. If you have any concerns, please talk to the chairs, or you can also talk to the ombuds team. If you have any specific concerns, the IRTF follows the same anti-harassment procedures as the IETF. And so even though we follow some of the same procedures as the IETF is a different organization because we conduct research and we focus on longer term research issues related to the internet. So our main goal is to develop and facilitate research discussion, research collaboration. We are hoping to spark some great discussions today. We are also able to publish documents, experimental and informational documents to be more specific. And in fact, we're going to talk about such documents in this session. But yeah, our main goal is collaboration and discussion. If you would like more information, there's an RFC linked out on this slide. And now for our agenda, we do need a note taker. Is anybody in this room willing to take notes, please? Thank you, Andrew. Okay. Right. So we have 3 presentations planned for today. And our first speaker is David Hayes. David has worked on transient congestion management in various contexts, including Swinburne University, University of Oslo, and Simula. In addition to this TCP evaluation suite that David's going to be talking about, topics include delay-based congestion control, shared bottleneck detection in RMCAT, a framework for deadline-aware, less-than-best effort service for bulk transfer, and reliable, consistent transport over cellular multi-millimeter wave networks. Sorry. And David is currently looking for a new position. All right. I will bring up David's slides. Whoops. And then pass slides control. All right. Floor is yours.
Well, good morning, everyone. So it is a little bit unusual to be presenting a draft this old. So, but why we're doing that? And I've been doing this talking to both Tom and Mohit because from the NS3 community, they've expressed some interest.
Microphone, please.
Please get closer to the microphone. Maybe we can.
Is it on? Yes. Okay.
Can probably make it a little.
Is that better?
Higher.
Okay. Okay, so Tom and Moa have expressed some interest in actually carrying out some of the intentions of this draft, but because it's so old and most people have forgotten it existed, so I volunteered to present what it is. So why does it exist? Because it was there to help fair comparisons between congestion controls.
David, can I interrupt you for a second? Can you adjust your microphone a little up, please? We have time. You don't even need a timer. Yep, yep. All right, and then make sure you're speaking into a microphone. Yeah.
Okay. Is that better? Okay, so it exists because we wanted to have fair comparisons between experimental congestion controls. And this used to be a very, very, very lively meeting in which people criticised each other's proposals, and there was no way of any fair comparison. So this is partly because of that. And what it isn't there to test standards-ready TCPs. It isn't an exhaustive test of every type of topology or anything like that. And it won't produce graphs for your paper. It's not its intention. You write a paper, you do your stuff. Okay, what it is a small set of standardized tests that have been very well thought out by a group of people, and we'll have a look at them in a minute, and made publicly available, meant to be negligible work for you to actually run and get some results, a small set of summary results, and there are suggestions on how this could have been modified into the future. And we're presenting it because there's been some interest from the NS3 project, specifically Moet and Tom, in looking at putting it into NS3. It's actually partially already there, and doing a few more things to it, revising the draft and bringing it back to life again. Okay, so the basic idea, first, this, although I may be an author of this current draft, this work has had an enormous number of people contribute at different aspects. So a lot of the ideas and tests came out of the TMRG and before, and people like Sally Floyd and Lars Eggert and Lachlan and a whole lot of people have done a lot of thought into some simple tests that make TCPs show certain characteristics. So I sort of brought the NS2 implementation together, but a lot of that was done by Gan Wang and Yong Xia, and there's been all sorts of other people who are involved. The basic idea is you have a test suite where you feed particular topologies in. You have special elastic traffic that you put in, not just single flows, thousands or sometimes hundreds of thousands of sessions. And you have your congestion control and you get a subset of results. It was done in NS2, but it was meant and designed so that you could make a test bed that did this as well if you wished. I'm going to go through quickly the topologies. Okay, if you want to go into the detail, please read the draft and have a look. You might wish to contribute. So it starts with what most people start with, simple bottleneck tests. Okay, they're probably not as simple as the ones you normally start with, because although there's looks like 3 sources and 3 sinks, it's actually bidirectional traffic. A lot of people only deal with one direction, and that bidirectional affects TCP. So it's bidirectional traffic, and each of those sources is really just a different delay and capacity away from the central link. Okay, they actually generate, if you're doing the data center one, possibly hundreds of thousands of concurrent TCP sessions to test with. Okay, in this particular test, all of the TCP traffic, so all of those hundreds of thousands of TCP sessions are running whatever congestion control you're proposing. Okay, and it looks at different loads, 60% to 85% and 110% of offer traffic load, and just brings out some simple statistics of link utilization, how many packets you're dropping, and what your queuing delay is. Now this is the latency-oriented test, so it's the same sort of thing. It doesn't go through all of those scenarios. Just sticks with the access link type 1. And you do tests with a standard TCP, whatever that standard TCP happens to be these days, and your own. And it looks, what it does is it changes the buffer size. So it sees how your particular versions perform with different size buffers from 0.1 of a BDP to 2 BDPs. And looks at throughput, packet drop, and average queuing delay, the same sort of thing, but it doesn't deal with AQMs, and more about that later.
I'm not sure.
I'm missing
You're missing.
all
Oh.
my pictures.
Oh no. Yeah, I didn't. I mean, I can reshare the slides, but
I have the pictures. You saw them.
yeah. Okay. Yeah, I don't know. Well, that's not ideal. Okay, let's see. Sorry about that. I mean, the other thing I can do is, right, they're all here. Okay, I'm gonna try reloading the slide set.
Okay, for those remote, there's a problem with the slides. In the PDF, they're there, but on Meteco, all the pictures are missing. So we're just trying to fix it.
Yeah. Okay, let me try. Okay, I don't know what's going on, but the other thing I can do is to share the screen. Okay, let's see if we can make that. Okay. Okay, you're gonna have to say next slide.
Okay, that's all right. So where were we up to?
So ramp-up time. That's one.
Okay, the ramp-up time, the same sort of deal. You have all your potentially hundreds of thousands of TCP sessions running as background traffic with a load of 50%. And then you start up 2 TCP sessions with yours, and they start at different times, and you measure how long it takes for them to send 1,500 bytes, 15,000 bytes, 150,000 bytes, and so on until the simulation ends. So you look at both TCPs and how they do. So it's a bit like a continuous completion time test in some ways. And that's one of the statistics you use. But rather than running it with lots of different file sizes, you just do the one, but measure how long it took to get to different stages. Okay, next, thanks.
Yeah, I changed the slide. Takes a while.
Okay, behavior with transient traffic. Now, this is the only one that uses inelastic traffic as the background traffic. Okay, all the other tests, it's 100,000 TCP sessions. So this uses inelastic UDP traffic as the background test and has a look at how TCP adapts to that traffic in the background. Okay, and it looks at different characteristics, how fast it can increase its window, and especially how much harm your particular version of TCP causes to the UDP traffic in terms of dropped packets. Okay, next, thanks. Okay, throughput fairness, and this is where you do an A/B type test. So each pair of those is running thousands of TCP sessions, but each pair runs identical ones that start at identical times. Okay, and you're looking at comparing your one with a standard TCP and measuring the difference against the baseline that you do. Okay, so it's a sort of a throughput fairness type test, but it's not the normal simple ones that you see with just one flow, another flow coming up. It's looking at it in a bit more realistic environment and seeing how it works. Okay, next, thanks. Okay, intra-protocol and inter-RTT fairness. So this is looking at how your TCPs fight each other. Okay, so again, you've got your elastic TCP sources as background traffic, and you have 2 test flows that start at different times, I think, and then you are measuring how they compete with each other, and you do it when they have different round trip times coming into the link as well. Okay, so how does your TCP compete with itself if one has twice as long a round trip time as the other, and that sort of thing? Okay, and the output's just a simple ratio of the 2. Next, thanks. Okay, now this is a multi-bottleneck text, and the main idea with this one is that you have a lot of different flows happening in the network, and what you want to be able to compare is if you've got a flow that goes all the way through all of the bottlenecks to the other side, how does it compare with the flows that only do one hop? Okay, so in the end, you get a ratio of the multi-hop one versus the average of the single hop ones. Okay, next slide, thanks. Now, all of these use something called tmix. Now, it doesn't have to use that particular thing, but tmix allowed you to be able to capture a real trace, and all of the traces in this test come from a real trace capture. You take your enormous PCAP file and you process it to get a session level or an application level, socket level interaction. So TCP on the left, initiates a session with TCP on the right, and then they both send a megabyte file to each other at the same time. Or this side sends 10 kilobits bytes to that side. After 10 seconds, this side sends 5 kilobytes back. So there are a few types of interactions that it tries to capture, but we need to do something like that because we're testing not against inelastic traffic. We want elastic traffic, so it's got to be the TCP running. So we need the TCP to be able to do its thing, not send packets at particular times, but start sessions at particular times that have particular characteristics and let them play out according to what's happening in the network and measure that. Okay, so it's a bit special. And when this was done, there was the NS2.1, there was the capture tools, and there was a mod to the Linux kernel that allowed you to set up a test bed and run this over test beds as well as traffic. The status now, I'm not so sure of, but that's why it was decided on in the first place. And most of the other test traffic generation tools you have don't actually generate this sort of traffic. But this is the traffic we need to test with, so that's why they did it that way. There was a lot of arguments with the original team, and I remember Lachlan told me the arguments. He wanted to have model-based because he likes models. But Sally Floyd was insistent that it had to be real traffic because that showed up things that you would never see with models. And she won. So that's why it is the way it is. And originally it was thought that every number of years they would do a new update of what the current traffic looked like and then feed them as new traffic traces into the system. Okay, so that's the idea of it. Now, to make this work with all sorts of different capacities is a bit more complicated because you want to keep the session times, you want to keep the sessions intact, but you want to regulate your rates or your traffic load. And that is done by regulating the time between when the sessions start. So you magnify or reduce the session start times, but you don't do anything to what happens within a session itself. Of course, if you have real traffic, then you have problems like you capture a huge amount of traffic through the day, but it changes dramatically at lunchtime compared to afternoon, and then when everybody knocks off work. So you end up with that, which makes it very hard if you're using that traffic to get any summary statistics because the traffic isn't stationary. So these traces are then actually divided into bins of about 10 seconds, depending on what capacity you're looking at, and then shuffled to remove that non-stationarity. So it keeps the short-term 10-second session times, and what happens inside a session, but then shuffles the rest so that you get rid of the non-stationarity and can have statistically valid tests. That's the idea anyway. Okay, so that's a special note about that and why it was used for these tests, because what traffic you test your congestion controls against is very important. If you test it against pristine, idealized traffic, then you will never see some of the problems it could have in a network like the internet. Okay, next slide, thanks. Now, since this happened, there's been a number of other works that have produced evaluation suites that generally don't test with the same topologies or the traffic. So they tend to be more simplistic topologies, more simplistic traffic. Generally speaking, TCUP helps you automate a test bed and run experiments and produce lots of graphs. So it's very nice for that if you're setting up a test bed and you want to do want an easy way to set it all up and manage it. It's really good. It came out of Kaya, where I used to work, and some people here as well. And Flint comes from Scandinavia, Sweden, I think. And it also runs test beds. I had a bit of trouble following some of the documentation there, but it has a bit more advanced traffic generators, not as advanced as the TNX type ones, but both of these only really test long-lived flows. Okay, remember the first tests in the evaluation suite, every one of the possibly 100,000 concurrent TCP sessions was running your test congestion control. Okay, so that is a bit different there. Now, Pantheon, I really like, came out of Stanford because they made it open to everybody. And you could give them your stuff and they would publish graphs and show where different congestion controls work. As far as I know, it's not running anymore because someone would have to fund it. It did some tests with real traffic, which was really good. It didn't do some other tests, which would have been nice, but if anybody was wanting to build something along these lines with some more advanced tests would be perfect for a test bed type thing. Okay. Now, the interested parties from NS3 would really like to know, are there any other ones that exist that nobody knows about? I know Moet has a private one in his university that eventually he's going to make public, but if there are, they would very much like to know about it because they don't want to reinvent things, but they see that there's a need. They think they want to do it in NS3 and update some of the characteristics. And if there's an NS3 one and a testbed one as well that can be comparable, then that would be really good. So if there are others, please let us know either in the meeting or on the mailing list. Okay, next slide, thanks. Okay, so while we were here in the first place, there's some people interested in updating this and wanting to have it as an available test. Okay, Tom, who looks after the NS3 project, he's really interested in building a community. Okay, he wants a community of like-minded researchers to be able to contribute to a tool and have it as a valuable part in what the community does. So he's interested in people letting him know on the list or directly via the email in setting up a group of interested people who can help with discussions about what it should be and so on, potentially new traffic traces, testing once they have different things to test, and implementing different aspects as well. Okay, so if you're interested in that, we really want to know. And the idea then would be that this group would get together, have some discussions and things, and maybe do a bit and report back at the next ICCRG. Because Tom would really like it to be a valuable international group of researchers, but within this context in the IRTF. Okay, now Moet has already done some NS3 implementation. So he's done some of this test suite stuff. There's bits missing in that, and he's on the call now. So if you have any questions, he'll be able to answer. And he is still going to plug away, but would love people to help as well, because he has students who are working on different things and he's happy to give them little bits. But if we would just rely on that, 20 years from now, it'll still be going this way. So he wants to be part of this group, Tom and him, and to have others and to have it contributed to something useful. Now, there are things that need updating, and there is always the elephant in the room, AQM. The reason why there was no AQM last time is because the only AQM that was standardized was red and nobody used it. So what do you test against? And everybody else kept changing what they were doing. So it couldn't be done. And I listened to the ICCRG at Prague and had a look when the AQM question came up, because they were proposing one that was a higher end sort of test for testing whether it was standards ready, that had some actually similarities to some of the things that were done here, but at standards level. So is it safe to deploy on the internet? That's what they wanted to know. And of course the AQM question came up and nobody could agree at that point. Now, yes, there should be some AQM support. It has to be a standard AQM. It has to be something that's used, but this isn't an AQM test bed. So it's not for playing with AQM. They're AQM test suites, you can do that with. Okay, and if you have a congestion control that relies on AQM, then of course you've got to test it with that. Okay, so that's gone without saying, but if we go down this rabbit hole, it may never come out again. So we have to be very careful there. It's never going to do every sort of AQM in every sort of scenario, because that's not what it's for. Okay. And Moat's quite keen of putting things like quick in and other types of congestion control. However, we have to be very careful that when we define what this is going to be, that it has strict borders. It can't do everything. Okay, if we wanted to do everything, it will never happen, which is why it was there for 10 years. So it has to have limits, and some things just can't go in, but having something that does most things in a nice comparative way is useful. Having something that does everything is not useful and impossible to maintain and update. Okay, so I think that's where we finish, and the rest is up to the community to decide what they want to do with it. Okay, we have some people keen to work and implement it in NS3, and if you want to be part of the discussions around what it should be as it's revised and that new work, please talk to the authors on this presentation and send it on the mailing list as well. Okay, so thank you very much.
Thank you so much, David. Building a congestion control testing community sounds like a great idea to me. We have 2 people in the queue right now. First up is Colin.
Hi, Colin Perkins, speaking as an individual. So yeah, I think this is really nice. I think it's a really good thing to have. I would agree with your comments about focus. Yes, I think ACM and all the CCN stuff would be a wonderful thing to do, but we need to keep it bounded enough that it actually finishes within the next decade. I think that would be useful. For the non-TCP congestion control, how much is actually TCP specific in this draft versus it's by default written about TCP because that's all there was at the time this was?
That's right. Yeah. It's not really, it's just looking for a reactive congestion control. Okay, it is specific in that TMIX was designed to work with TCP, but anything that could read an application interaction file and process it could work. So it doesn't have to be TCP.
Yeah, so I mean, my feeling is that adapting this to give a set of test cases for Quick, for example, would mostly be a case of change TCP to Quick throughout, and there wouldn't actually be any technical changes to the work. So it may be maybe it can just be phrased, change the phrasing to be slightly more generic and write some words in the introduction. That probably isn't a very big change, whereas I suspect the ECN support is a much bigger task.
Yeah, so which is why there's the red marks there and
absolutely,
so on. Yeah. Because even ECN, which one? So
yeah, absolutely. But I think if it's easy to update this so it's general enough to support Quick, I think that would probably bring in a lot more interest as well.
Yeah, so that's the idea that Moed and Tom had as well.
Great, thank you.
Great. Next up is Zili, please.
Zili from Hong Kong UST. Thank you, David, for this very nice talk. I'm wondering, have you ever considered of the traffic patterns on the effect of congestion control? Like for video conferencing, we are going to send the traffic by video frames instead of a continuous traffic, right? And we did several experiments before, which shows that they have a significant impact on the performance of the congestion control. So do you have any considerations or plans on that?
Me personally, no. But when we look at the traffic in the new one, we have to update it to what's happening in the internet now. Okay, so there is a proportion of inelastic and elastic traffic going over the internet, and we have to look at that in how we work our traffic. Okay, so that is important, that what we do, it's not going to be exactly what happens in the internet, but matches the important characteristics that we want. So with regard to that, yes, we would like to have the same proportion of traffic. How we do it is undecided, and if that traffic is congestion control, can it be modeled by an application layer type thing as well?
Right. Maybe a comment is that we can try to, or maybe I can help us try to add this kind of evaluation into the draft, because it is similar to the on-off application in the NS3, but not exactly the same, because that video conferencing is elastic. It is not inelastic.
That's good. Well, that's very good, and I'm sure that Tom and I will love to have you work and contribute that. And of course, the other step is that this comes from real traffic. So we have to take the real traffic, measure it, then convert it to the application sort of level. So it plays out by the congestion controllers, and perhaps there's other traffic in the background doing that sort of stuff as well.
Right. Maybe a follow-up question is, not only, let's say, the video conferencing, but also, let's say, for web traffic or this kind of backup, they all have different patterns. So maybe we can all push them into this suite, or is that not a part of this draft?
I think that will be for the discussion group, because it has to have, it can't be everything, okay? And the question that people will be asking is, if we put this traffic in, how is it going to change the, is it going to change the dynamics in an important way? And if it is, and it's needed, then they will look at doing it. And if it doesn't, then perhaps not. Okay, but they can't do everything.
Thank you.
Thank you. Next is Shiva Raj.
Siva from Daikin. Yeah, thanks for resuming this, David. In some way, we have been missing it in some way.
Who deserve the thanks
Yeah,
for resuming
so
it. I'm here because of them, rather than the other way around.
So one thing that came to my mind is like, yeah, there has been a lot of moves towards new congestion control. Like, for example, if I want to have like simulate or do kind of experiment in the world in NS3 of a very simple case like BVR version 3 over Wi-Fi, I think Wi-Fi is already supported, like 802.11x is already supported by NS3 in some way. So something like this will fall within the scope of this draft.
This does have a Wi-Fi test for the first scenario, but yes, the idea is it should be very light for someone, so that if they have developed a congestion control that they're testing, they should just be able to plug it in here. They don't have to do any of the other stuff. It should just run and give them their results. So ideally, just take the actual congestion control.
So in a nutshell, the background traffic and all those things are already like kind of set up. If I want to run BBR version 3 over 802.11x, then I need to plug BBR v3 there.
Yes, so if you were running the wireless scenario here, you would have BBR3, and it would be running for every TCP session that goes.
Sure, thank you, thanks.
All right, and then we have Christian.
Good morning. Good morning. Wow.
Good morning.
There's a weird hiccup going on there.
Yeah. You're pretty loud.
Is it me? Is it?
I don't know. You're just coming on like a little loud. If you can turn down your mic a little bit on your end, please.
Does it work better like that?
Still the same to me.
Oh shoot.
Oh, you're fine. We have time.
Okay. So the question I have is whether you have been looking at the work going on to rewrite RFC 5043 that defines the criteria for congestion control protocols. I mean, we have a version B that is in progress, and the version B describe a series of criteria that would expect a proponent of a new congestion control protocol to check. And there are things like what you describe, of course, but there are some specific things like testing the competition against existing congestion control protocols. So, for example, test against Rhino, test against Cubic, see what happens when you compete. There are things like testing whether the new congestion control protocol protects against buffer bloat. Testing against a series of well-known AQM where we cannot do all of them, but it's important to check that at least the standard ones, a couple of them are tested. And then there's also testing against some real-time control protocols, I mean, RMCAT and things like that, which are well known. So these are details, but I mean, the general idea is that it'd be very nice if someone who's in the process of defining a new control protocol could try to use the tool and assess the criteria specified in 5043 bis.
Because this has a common background in Sally Floyd, they have similarities. So all those tests you described in some relation are actually in the suite.
Yeah, no, it's there is actually a departure from Sally Floyd in the 5043 bis.
Okay.
The departure is that there was a lot of emphasis in 5043 about equity of bandwidth. But the change of emphasis is really do no harm.
Yeah.
And it doesn't mean equity of bandwidth. I mean, it's largely lesser emphasis on that. Because, I mean, it's hard to measure. But there are things like not causing packet losses for other protocols, or not causing the delay experienced by the other protocol to increase, or I mean, limiting the way in which they increase. Not causing buffer bloat. Things like that are important.
So even though this is 10 years old, there are actually some of those elements already in there. So, but we hope the committee will refine it and bring in some of those ideas that you're talking about, maybe more strongly, the latency type ones. There are latency tests in there. But the important thing with this is is never meant to test whether it's internet ready. This is meant to provide a good comparison of thorough tests between new experimental congestion controls that are probably a long way from where they get to the CCWG.
Yes.
So
still, it'd be very nice.
Yeah. Well, thank you.
Okay.
Agreed. Thank you, Christian. So to me, it sounds like there is a good amount of interest in testing congestion control, and there's lots of great ideas. And honestly, I'm reminded of why we have CCWG is because congestion control has changed and the internet has changed over the last, such and such many years. So I see this as a kind of a cause of why we're getting all these additional things brought up now. I would like to do a show of hands. Because I'm curious who is interested in doing work in this space, and work in this space can mean contributing to this particular implementation, testing this particular implementation, or it could mean showing up at a hackathon, for example, in Vancouver, and talking about different test beds, different testing tools, and things like this, kind of in a test bed and a simulation space. So who is interested in doing work in this space? And I'm going to add in ICCRG. And I would see a Vancouver hackathon scenario as sort of ICCRG congestion control testing table kind of thing. So if we can have just a little gauge. And then if people want to enter the queue and tell us specifics of what they're interested in. Okay, we have 8 yeses so far. That's pretty good. Okay, 9, 10. Oh, that's cool. Okay. That's not too bad, given we have 46 people in Medeco. 13 people said yes. I'm going to terminate that now. All right, and I guess we don't have to figure out all the specifics now, but
Yeah, I think it would be good to have a small discussion group, either start on the mailing list or another mailing list to start aspects and to define with some firm ends how this is going to play out.
sounds like a great idea. David, would you mind sending an email to the mailing list to seed this discussion, please? Awesome. Is there anything else? I'm going to stop sharing my screen now. Okay, so we have 2 more talks, and next I would like to invite Zili up, and let's hope that your slides are going to show as expected. Okay, you should have control of the slides now.
Okay, hello everyone. This is Zili from the Hong Kong University of Science and Technology. And this is my first IETF, so I'm wondering if the ICCRG will be the appropriate place for me to present the work on the, I think it's kind of AQM, but we would rather say it's trying to investigate how to feedback the congestion control signals into the NHOS. This is a paper published in the SIGCOMM 2022, and we made some minor updates after that. So I will presumably skip the backgrounds here, because the ICCRG, I think, is mostly familiar with all of the congestion control stuff here. Right, so this work is mainly focusing on the wireless tail latency optimization. So as we may all know that for the internet compared to the wireless, especially the Wi-Fi and cellular, the average latency or the median latency might be the same, but the tail latency in the wireless network is much worse than the cable networks or than the Ethernet. Okay, but the question here is that in the wireless network, one thing that happens very frequently is the bandwidth drops. Let's say here is the incoming flow, and the flow arrives at the router, and the downlink capacity of the wireless router might be fluctuated by a lot of factors. Maybe the microwave, maybe another user competing or interfering in the same channel. And we had a measurement experiment back to 2 years ago showing that for the wireless network, the bandwidth fluctuation, or in another word, we measure the bandwidth in several times loss, and we calculate the ratio between the 2 bandwidths. It's much more fluctuating than the Ethernet. So you can see here, for the wireless network, if you calculate the bandwidth in the slot of 200 milliseconds, it is very likely for you to see the bandwidth drops with the ratio of 1/6 to even 1/50. But this same number for wired network is only 1.5. And this can actually result in the very severe delay jitters. I will show you an example here. So this one is the abstraction of the end-to-end transport on congestion control. And the left side is the sender. The right side is the receiver. Let's assume it's a sender to receiver delivery flow. For example, the cloud gaming or video on demand streaming or things like that. So basically the traffic will first go through from the sender to one router in the middle. Maybe let's denote, for the sake of the simplicity, let's denote this as the last mile access point. And this access point will convert the traffic from the wired cable to the wireless network. But here, when this access point is congested, the queue in the last mile access point will be formulated. As you can see, there are 3 gray packets in the queue. So how could this signal be known by the sender? Because we know that the access point itself, it is the congestion point, but it can do nothing. We need to rely on the congestion control to react to the network congestion. For example, reducing the congestion window or reducing the sending speed to finally alleviate this congestion in the network. So this information needs to be somehow carried back to the reaction point or to the sender part. So what are the current practice in the TCP congestion control is that, okay, let's say for example QB or COBA or like whatever delay-based or loss-based congestion control algorithms, there will be another packet joining the queue and suffering a long latency. And this packet cannot directly tell the reaction point, which is the sender, that the network is congested. Instead, this packet needs to first wait in the queue and then leave the queue to the receiver. And the receiver sends back an acknowledgement. And when the acknowledgement goes back to the sender, can the sender finally knows that, okay, maybe the delay is going up or the blue packet is lost because let's say QB relies on the loss-based detection. So no matter which mechanism the sender is relying on, the sender needs to know the information only after receiving the acknowledgement after the congestion happens. But you can see directly from this diagram is that the red part in this whole congestion control feedback loop is redundant. If there's some way that you can directly tell the sender from the access point or from the router, the congestion will be to a very most extent be elevated and reacted in a very short time. And especially when we are talking about the last mile or we are talking about the wireless network, when we say the latency goes up from the 50 milliseconds to the 500 milliseconds, the additional 450 something is mainly from the last mile, right? In the core network for the high performance switches, it is very hard to store a packet for 400 milliseconds. We do not have that deep buffer. So of course, we know that congestion control here cannot solve the problem itself because congestion control is passively listening to what is happening in the network. So what should we do? In fact, there's a very long history in the congestion control or even AQM or even internet in the last 30, 40 years. There have been a lot of effort trying to do that. And the most straightforward way is just to, somehow let the information be carried back by kind of control message. If you can think in the link layer, we have the PFC, and even in the TCP, we have a lot of different previously designed, like XCP, RCP, related algorithms or protocols to tell the sender that, okay, congestion is happening. And this can actually eliminate the inflated control loop. But the question here is, if we want to design the new protocol and let the router tell the sender what is happening in the network, we will need to modify both the router and the sender, right? We need to modify the router to carry this information to a specially designed packet. And the packet needs to be understood by the sender, and the sender can finally decode what is happening in the network. That will require the modification on both sender and router. Unfortunately, this is what IETF is doing for the last 30, 40 years. And we have hardly see any improvement because sender is maintained by the content providers, like say Netflix or like Google, Microsoft, and so on. But the router is maintained by the router vendors. It is very hard to get these two parties on the same table and to synchronize. You need to have this new protocol deployed. So what are we going to do instead? We are going to do is that can we only modify the router to carry this information back to center, but without modifying the center at all. So that means we need to modify the router in a way that the modification is scalable to most of the congestion control algorithms, and let the congestion control algorithms react to the network congestion. This is still challenging, right? We have so many different applications in the video conferencing, or we have also cloud gaming, maybe in the future VR, metaverse, and those fancy words. And we also have many protocols, TCP, QUIC, and also in the WebRTC, we have the RTP related protocols. And later, we also have a lot of congestion control algorithms which rely on totally different signals. We have the algorithms relying on the delays, delay gradients, packet loss, and also BBR based on the risk, right? So many different algorithms. So how are we going to do that? Let's first dive into what is happening here on the last mile router. So previously, the center, this is what I extract the last mile router from the whole end-to-end abstraction. The router on one side connect to the center side using the cable network, and on the other side is going to deliver the message or deliver packets to the receiver through the wireless network. And we separately call them the downlink and uplink. Usually the sender sends the data packets to the receiver in the downlink or downstream direction, and the receiver will send back the acknowledgement packets in the upstream direction. So what we are going to do is that we are going to modify the feedback packets, or in TCP's case, acknowledgement packets, but not modifying the original data packets, to let the acknowledgement packets know that, or let the acknowledgement packets carry this information back to the sender. So we will have a feedback updater. And we also have a fortune teller, which will tell the feedback updater what is going to be updated or what is going to be modified to the sender side. So put it in a simple word, what we're going to do here is to coordinate the flow in two streams as a whole. And when the downstream packet is experiencing the congestion, we are going to modify the upstream acknowledgement packets and let the acknowledgement packets carry this information earlier to the sender side. So we actually, in the paper, we separate this into two types. One is we call it out-of-band feedback. The other is what we call the in-band feedback. And the difference here is that the out-of-band feedback, in the out-of-band feedback, the feedback packet carries nothing, no information. It is the sender that received the ACK. And they check when we send out this packet and when we receive this exact packet. We calculate the time difference that is known as the RTT. And they use this for no matter what algorithm is doing for. But for the other type, let's say the RTP, RDCP packets, they are using the in-band feedback, which means the network information is encoded into a separate feedback packet. And this feedback packet will put all the information into the payload, and the payload itself carries the information on the network. So here I'm going just to focus on the TCP case because we are mostly the TCP congestion control working groups here. So our solution to the TCP-based congestion control algorithm is we are going to delay the X. We are not going to modify the X. What does it mean? I will show you in the next slide. So let's say we have a packet number 9, packet with the sequence number 9, going from the sender to the receiver. And when this unfortunate packet number 9 arrives at the congestion point, it is going to experience a congestion. And we know that all the ways that this packet will first go to the receiver and be acknowledged by the receiver, and finally when the sender received ACK10, can the sender finally knows that the congestion is happening. And this is too late. And what we are going to do is that when this packet with the sequence number 9 arrives at the router, we know TCP is bidirectional, right? There are packet number 9 arriving in the downstream direction to the router. There are also other previous acknowledgement packets going back to the sender. Let's say in this case, the X3 and X4. They may be concurrently arriving at the same router, but just in two directions. So when the packet number 9 arrives in the downstream direction from sender to receiver, what we are going to do is that we are going to delay the ACK number 3 and ACK number 4 to let the sender know that something must be wrong in the network because you remember that our ultimate goal is to reduce the sending rate of the congestion control. So as long as we can, you can call it as a DC or whatever, as long as we can make the sender believe that the network is being congested, then that is already satisfying our goal. So what we're going to do here is that we are going to, if the, I had an animation in the PowerPoint version, but in the PDF I can only show it in this way. If the ACK number 3 and ACK number 4 arrives at the router simultaneously, we are going to let ACK number 3 go. Okay, it's not, it's showing the same page. We are going to let ACK number 3 go and hold ACK number 4 for a few milliseconds. That is not supposed to happen for the delay from packet 4, right? But we just want to hold ACK 4 for a few milliseconds. So when the sender receives this delayed ACK 4, the sender will know that the RTT is increasing, or I will show you later the rate is increasing and so on. This is what we call the implicit congestion notification, because we do not have any explicit flag or explicit markers on the packet. We are going to let the ACK packet itself carry this information back. So how is going to work with all these different algorithms here? Because they rely on the delivery rate, delay gradients, RTT, and so on. So the one important information here is that we think all the congestion control algorithms, what they are doing now is just to receiving the ACKs, right? For example, BBR calculates the delivery rate. What is delivery rate? They have a sliding window. In this window, how many bytes are sent out? How many bytes are acknowledged? They use the total number of bytes over this length of window. They know the delivery rate. For GCC, which is the most widely deployed WebRTC's congestion control algorithm, they also use a delay. They just measure the delay gradients, the difference of delay between two packets. So no matter what algorithm here, like COPA or NADA-Script, no matter what algorithm here they are using, the information is processed from the ACK packet itself. So as long as we delay the ACK packets in a specially designed mechanism, the congestion control algorithm will know that, okay, they can predict what is happening in network. So what we are really doing here is that for the last mile access point, we can actually estimate when this blue packet arrives at the queue, we can estimate when will this packet be delivered to the receiver side. So in this case, the delivery time, when this blue packet just got in queue, we can estimate the delivery time should be the queuing time plus the transmission time over the wireless links, right? So the queuing time will just be the queue length over the transmission rate. And the delivery time can also be somehow fetched from the wireless drivers. So we can estimate this and know that when will this blue packet be fed back. And after that, we know for the previous packet, let's say it's going to be normal. It's going to be a blockless and very smooth transmission from the sender receiver. And for this blue packet, it's going to suffer packet queuing delay. We know the difference on how long the additional delay it will be. We apply this time difference in the reverse direction over those ACK packets. So if you want to understand from the center side, the blue line here, the blue dotted line here is before packet, let's say packet ACK number K, the delay just as normal as it should be. And after packet number ACK number K, the delay gradually goes up. And what our ICN is doing that we are going to push this curve forward by letting the ACK packets with the smaller numbers to carry this information back. In this orange line, the ICN method will try to let the sender know the delay increase earlier and react earlier. And we will show a lot of analysis in the paper saying that this will help to alleviate this congestion, especially those transient congestion, by many times. Okay, yeah, so for delay-based CCAs, the rate will just naturally go down by seeing the increase at the rate. And for the rate-based CCAs, let's say the BBR, what we are doing here is we are going to stretch the intervals between the ACK packets to let the rate samples decrease. And the PBR will also react to decrease the center rate. Okay, I will just going to skip the evaluation part because sure it's going to be good, right? We publish paper, so we can always find a way to show that our evaluation is good. But basically, I want to tell you that we compare with different AQMs, and we do test several CCAs, including TCP-based and RTP-based. And we all see that we can reduce, what we're going to reduce here is that we're going to reduce the ratio of the stalls. We define stall as the RTT going above 200 milliseconds. We can reduce the ratio of the stalls by almost a half compared to the previous AQMs on different congestion control algorithms, including COPA, GCC, and if I remember correctly, also BBR.
No, I'm
also
not
maybe
seeing
ABC in that paper. Okay, I'm gonna stop here, and I'd like to welcome any questions or comments and see how this research group is interested in this kind of work. Thank you.
Thank you, Zili. And first we have Vidi in the queue. And Upper, can you please unshare your video until it's your turn? Thanks.
Thank you, Zilly. I was very careful listening to this because this is what I work on. I think it's an interesting idea, but I was thinking about if you delay, let's say, packet number 4 on the ACK path, is it not gonna, let's say packet number 4 was for, let's say, HTTP, it was the end of one of the resource. Now you're delaying 4, which means if this resource could have been loaded 10 milliseconds earlier, you're delaying that. So it has an implicit effect of, if some of the HTTP resources can be completed earlier, now they're going to be delayed. I'm not saying it's always going to happen, but like how HTTP resources are divided into different streams for quick or by sequence numbers.
Right, that is a very good. Sorry, go ahead.
Yeah, so that's one point. The second point I thought about was Cubic doesn't rely on increased delay, so the loss-based congestion controllers are still at a loss. Just pun intended. So how do you solve this problem for loss-based congestion controllers? And the third point I have is delaying the ACK can also cause probes to be sent out from the sender. The tail loss probes that, if you wait for an ACK for a certain time and you don't get anything, either the probes are going to get sent out, or if you wait long enough, then it's going to cause an RTO. I'm hoping this will not cause an RTO, but just a thought.
Right, all these 3 questions are very good questions. So I think the first one, third one are basically how we are going to delay the X. So for how we are going to delay the X, we actually set an upper bound. So our point here is we are not going to delay the X for a very long time. We just want the sender know that the sender must reduce the sender rate. So from our experiment, as long as we delay the X by 5 or even several milliseconds, the sender is sufficiently enough to detect the congestion network. So that should be good enough. So we are not going to delay the ACK for, let's say, 100 milliseconds, 20 milliseconds. No, that's not the case. That will trigger the RTO. That will trigger a lot of bad scenarios. We just want to delay the ACK for a few milliseconds. And for loss-based congestion algorithms, this is not what we cover in this paper, because we are designed for those delay-sensitive applications. Let's say video conferencing, let's say cloud gaming, VR. And from what I try to understand, they seems not to adopt those loss-based mechanisms, because loss-based is known for high throughput, but also high delay as well. So here we are going to go focus on the delay-based, rate-based, or those congestion control algorithms designed for the delay-sensitive applications. For Cubic, I do not have any solutions here. I'm also eagerly looking for any other potential alternatives as well.
Okay, thank you.
Thank you, Vidi. And now we have Alper.
How much time do I have?
Just a quick comment. I mean, we have a little bit of time, but we also have a bunch of people in the queue.
Then I should introduce myself. My name is Alper Kamil Demir. I am from Turkey, Adana Alparslan Turkish Science and Technology University. I am working as an associate professor in computer networking. I am very happy to be part of Internet Engineering Task Force event. I am very excited. I know Christian Huitema for his contributions in congestion control and networking. I don't know Shiva Raj and I don't know Randall Jesus.
Alpa, can you ask a question or make a comment about Zeli's presentation specifically, please?
Or maybe we can chit chat later if you.
Because that is what where we're at right now. We're talking about the
Could you
presentation.
please explain what implicit congestion notification means?
Sorry, could you say that again?
I am revising my question. What implicit congestion notification has to do with shift the delay curve forward?
Oh, right. That's a good question. So here we are going to apply what we are going to measure on the downstream and apply the delay gradient to the upstream. That is what we name as the implicit congestion notification. We used to have a Chinese name in the paper, which is called 诸葛, but it's very hard for the non-Chinese speaker to pronounce, so we finally changed the name to ICN here. Because it actually pronounced as the 诸葛, but some people will say that they huge and think it's not hard, not easy to coordinate with each other. So ICN is not a kind of notification. It is not a specific, it's not an explicit notification. It's just going to apply the delay gradients in the reverse direction, and that's it. The mechanism called ICN.
Thank you very much. And your name is Juk?
Our speaker's name is Zeli Ming, if that was your question. You can find the agenda in the data tracker, which has all the different presenter names and all these things, if you're interested.
Thank you very
Now-
much for giving me time for talking.
Sure. All right, now let's move on to Shiva.
Thank you. Thanks. Yeah, I think part of my question has already been raised by Vedi, but I didn't hear a clear answer on you have delayed that, but have you studied the impact of that in other metrics? Like what is its impact in throughput or maybe your other quality of service metrics?
You mean MAC address?
So there is some kind of injected delay, right?
Right.
Implicit delay
Right.
injected in this framework. So what
Right.
is its impact in the performance? Is there any trade-off or you have not seen any trade-off yet?
We do not manipulate the packets inside or the packet formats. We just check the headers and cluster based on the 5 tuples.
So let me clarify my question. I don't think that you understand what I say. So you have delayed the act.
Right.
So what is its impact on performance?
Oh yeah, for example, COPA or GCC, they will reduce the rate when the network is congested.
So that means we are injecting explicitly, deliberately making the network congested, right?
Well, we are
So
trying to.
naturally it's not there, but you want to inject an extra congestion there.
Well, we do not inject extra congestion. When the congestion really happens due to the bandwidth reduction, due to many other factors, we want the center to notice as soon as possible.
So
Because-
that is already there in existing networks. So why we need to delay the packet more?
Because they are not still knowing that as very fast. They are still waiting for the whole congestion loop, and that loop will be further aggregated or amplified by the congestion algorithm.
Yeah, and we are further delaying it.
We are this minor further delay.
Yeah, a small millisecond.
Right, we are going
but
to
further
delay
delaying
for
it.
5 milliseconds and save for 500 milliseconds.
Yeah, I'd like to say what will be the performance without ICN and with ICN, if you have any. That will be great to see the performance change.
Sure, of course.
And my next question is, I think this is partially answered. Thank you. Regarding AQM, have you tried with Alpha-S?
Oh, we did. The one very basic issue for FIS is still rely on the end-house information.
Okay.
It relies on the whatever you call DSCP or the eSIM bit. It still relies on the end-house cooperation, which is not very deployable in the real world.
And in your paper, we can still see.
Yeah, we did compare that in the later version of this paper.
Oh, okay.
Right.
So is it on the improved version or the published one?
It is already public. I posted on the archive, and we can also discuss offline if you
Sure,
want.
sure. Thank you. Thanks, Sally.
All right, thanks. Next is Christian.
Well, thank you. That's a very interesting presentation because indeed the problem of getting feedback from the network quickly is something we would want to see. I have two questions, in fact. The first one is, have you considered doing like an equivalent of ECN? ECN will flip a bit in the header if it sees congestion,
Right.
but suppose you could pick another bit in the network header and flip it if you see congestion in the reverse path. Have you tried doing something like that?
Yes, for short yes, we did try that. And the good thing is that ECN can effectively reduce the delay. But the bad thing is many congestion control algorithms do not support that.
Yeah, it would require work in each
Right.
implementation, yes.
Right.
But still, in the long run, I mean, that work will be very useful. The other question I have is that there is a nasty congestion scenario in Wi-Fi that we are seeing, especially when doing media over Wi-Fi. And it's that the Wi-Fi card will sometimes just stop. What it does, it suspends the transmission channel. It uses the radio to go poll the other channels to see whether there's something better to do. And typically 100 milliseconds after that, it comes back and then all the packets are arriving at that point. But for implicit congestion notification, it's a bit late because we had no packets flowing in the other direction either.
I see what it is.
I mean, did you test that specific congestion scenario, or do you have any idea on how to handle it?
That is a very good question. We encountered exactly the same thing when we were trying to deploy this in the Linux kernel. So sometimes even for Wi-Fi, there is no even packet coming back in the reverse direction, if that is what you are referring to. And
yeah,
right. Our solution, like not very beautiful, but I would say kind of dirty solution is that we just wait for the first packet to come in. And if you do not, we can hold the previous packet from the other flows or from the other users as long as they go into the same direction. So basically, put it simply, we have no straightforward solution for that. And it is happening. It happens all the time.
Yes, it's actually the nastiest thing we have on Wi-Fi.
Right. So for those scenarios where there's no packets from reverse direction, this ASIN cannot address that. We are still hoping there are some packets coming back, no matter they are right 50 or
I guess
30.
I guess something we could have for further work, but it'd be very nice if there was some research going there.
Yeah, that is a very good question. Yeah. That is exactly the real problem we are encountering.
Thank you.
Okay, then I think next you have Randall.
Okay. Very good presentation, very interesting. I can definitely see that there's some potential here. One comment that you should probably take a look at testing against leadbat, since it's also delay sensitive. And the other one was, the question was how you're handling WebRTC and related protocols in terms of, since they're not ACK-based. Could you give more detail on that?
Right, paper does have more details. I didn't present here today, but pretty simple, we modify the payload.
Okay. And
WebRTC relies on the payload, yes.
Okay. And yeah, I guess those packets wouldn't be encrypted normally, so that would work. Yeah.
Right.
Yeah, okay, that does depend on the exact format of the payload and identifying the flow as being that, which could get interesting.
Right. We were thinking about maybe there are some asymmetric crypto which allow some routers to modify, but that is just thoughts. We have not done any experiments over that.
Right. Last point, and then I'll get off. Have you thought about whether it's possible or smart to try to do this and also provide ECN for protocols that support ECN, or would you get a double impact that would cause problems?
Actually, yes. For Scream, I think it is ECN capable protocol algorithm. So we did try, but this is not a part of paper. For those ECN capable and also delay aware algorithms, we do see some additional performance benefits. But the whole storyline here is based on the assumption that we do not want to modify the center side. So we do not cover the ECN things here. We still believe that ECN you need to modify the center or make the center support the ECN.
Okay, thank you very much.
Thank you. And now, Alper, do you have another question?
Yes, I have another question. Can we go back to slides where you mentioned rate-based and delay-based?
Oh, not here. Oh, should be.
Before that. Yeah. You say that there are delay-based congestion control algorithms and rate-based congestion control algorithms. Can you name protocols standardized by Internet Engineering Task Force based on delay or based on rate?
Protocol there are we can take the question offline, but there are BPR for rate based if you want to know, and the COPA GCC for delay based. Maybe you can take more questions offline if you want.
Can you share your email with me?
Sure. You can just find my name on the internet.
Okay, Zili, are you fine taking Thomas's and VD's question, or would you rather take the rest offline?
Oh, sure, whatever.
Okay, we have Thomas. Yeah, we still have some time. We're fine. So Thomas, please.
Hi. Thanks for the presentation. Can you go back to the slide that we just had before?
Sorry, which one we were?
It's basically where you had like 3 and 4 and 9 packets.
I see.
You could see. So it mentions it as a last mile access point, right. And we know people build all sorts of weird stuff with their networks. What happens if it's not the last mile access point and you like kind of have this linked in a row? Does this have any bad side effects of like the delay kind of like building up because all of the middle boxes apply the same algorithm?
That's a very good question. So one point is that it will only add up delay when there's a congestion. So what I assume here is if there are multiple bottlenecks in the line, right? So if there are multiple bottlenecks in the line, and happily they all deploy the same mechanism here, it is possible for delay to add up. But from what I see is that for the core network, it is, I would say, impossible to modify the routers. So in the core network, it's very hard to deploy this mechanism.
Right. So if I understand correctly, this is not actually deployed in like users' home routers or anything.
Just in the home routers, we modify the home router and we can get it. But for the core network or even ISP backbone network, it's, I would say, very hard to deploy this.
So what if I have multiple like access points at home, like linked in a row? Doesn't like the congestion that happens at the very end, like kind of make the delays add up throughout the routers?
If there are multiple congestion points, the delay will add up. But if there's only one congestion, no matter which place it is and how many routers will deploy this mechanism, there will only be one delay add up. It will only be add up at the point of congestion.
Okay, thank you.
Thank you. VD?
Hello, back again, sorry. I was just listening to other people's question, and I kind of feel like, let's say you delayed the packet number 4, which was in the ACK direction, and when packet number 9 is acknowledged, it will also be delayed. Could this be causing like the double congestion events at the center? Because one you artificially delay and one you delay because there was congestion.
Right, that's a very good point. So that's why I have this plot here. So you can see if for the, let's say, packet number k plus 3 or something, if it is already delayed, then the difference between the current packet delay, let's say k plus 3, compared to the previous packet delay, let's say the k plus 2, will be almost 0. So that packet will not receive any additional delay. We only apply the difference of the delay to the reverse direction.
I get that, but if let's say that difference is very high, then you could trigger other mechanisms at the center. But you said you only apply a very small amount of delay. So it's hard to say
We add
if
an
this
upper
delay.
bound of delays, right?
Right. So it's
10 milliseconds.
it's hard to say that k plus 2 or k plus 3 will not have more delay than what the orange line is saying, right? So you could
That's
have
true.
multiple. Yeah. So I think the idea where Christian said you could flip a bit instead of adding, like, there were initially, there were proposals to drop packets to indicate congestion. That's a very bad idea because you don't want to drop packets. So your idea is obviously better than dropping them. It's like delaying them. But I still think instead of artificially showing congestion, it might be better to flip bits instead of delaying or dropping packets. It could be the ECN bit. Maybe you don't flip the ECN bit on the sending path, but you could flip the ECN bit on the acknowledgements path. Yes, it's going to apply to a different packet, which is not experiencing congestion, but I think it serves the purpose of making the feedback faster. I haven't thought about this thoroughly, but as you know, you were worried about ECN not being adopted. It is getting adopted in many implementations. So I still think artificially delaying is not. It could have side effects. That's what I think.
I totally agree with you on it.
Thank you.
All right, and then we have Jonathan.
Hi, Jonathan from Deakin University. Thank you for the presentation. Very interesting work. I'm just wondering, have you ever tested the queue management scheme using multi-queue, so say FQ Codel, with there's already an inbuilt prioritization for sparse flows, and how does artificially delaying packs or packets impact the latency estimation algorithm, etc.?
That's a very good question. Not in this paper, but we have follow-up paper on archive testing with different AQMs, fair queuing, and not only AQM, also buffer management mechanism, fair queuing, strict priority, and so on and so forth.
Great, yeah, have a look.
Yeah, right, and it is still showing that they are trying to solve different issues. So for the different fair queuing and prioritization, they are trying to solve the issue of the flow computation. There are multiple flows compete in the same router. Here we are going to solve the issue of the link capacity drops.
Right.
So they are, you can think is one in the layer 2 issue and the other is in the layer 3 issue. So they are kind of orthogonal to each other, and you have the benefit of both by using both strict priority and also our mechanism together.
Wonderful, great. I will look into the paper. Thank you very much.
It's already posted on archive. You can just take a look.
Thank you.
Thank you.
All right, thank you everybody for this great discussion. Now, we do have one more talk on the agenda. However, our speaker didn't show up, but this is about an adopted talk draft in ICCRG. So we figured we could just share the slides to update everybody what's going on. And Vidi is willing to talk us through these slides. Vidi, I think you should have control of the slides.
I actually always forget how to do that.
Yeah, just left and right button should already be. Oh, wait, no, I have to pass you slides. I'm sorry. I didn't realize I had
Okay,
to
now
pass.
I see it.
Now.
Thank you. I'll just go. These slides were prepared by Marcelo, who's the author of one of the authors of Receive Lightbat draft. Receive Lightbat is basically, you apply Lightbat in the receive direction because it's possible that the sender or the server is not aware that your flow is a background flow. So as a client who's receiving this data, let's say an iPhone or an Android phone is receiving this data, it can apply this algorithm to yield to competing traffic. So sorry, I gave the intro before even moving the slide forward, but that's basically the idea. Rather than receive direction, the receiver is basically controlling the sender's rate to receive window, which, like the receiver has full control over receive window by advertising the receive window in the TCP headers. And the use case, as I explained, this is like CDNs don't know if this traffic is supposed to be background. And then proxies also don't know. So this is a very good use case of this. All right, so implementations, Windows 11 has RLED BAT since 2023. Windows Server has RLED BAT since Server 2022. Linux implementation, there is an open source implementation available in Linux. NS3 has it too since 2020. What's probably missing from here is macOS also has received LEDBAT for TCP. So just a add-on. Blah, blah, blah. And then I believe some initial experiments have been reported in this research paper. So on our request, the authors updated the draft to the more recent version 6. And they have added a security consideration section. And there are a new section on experimental considerations that would include also, right, so this is ICCRG group. So it would be good to know what is the intention of this draft. Are they planning to run a experiment or trial for some time in the ICCRG as an experimental status for the draft? So this is something they have added in the draft in version 6. Next steps. So this slide is blank. I'm going to assume the next steps for the draft are we ready to adopt this draft in the working group? And how many people, like we can do certain polls for this one. Reese, maybe we can do polls about adoption if people have read the draft and if they're ready to, do a review on it. So things like that.
So based on what I can see in the data tracker, actually, we have already adopted this. Wait, or LEDBAT? Have we? Yes. It's an active internet draft. It says draft IETF ICCRG. It was well before both VDs in my time as chairs of ICCRG. So I guess I would like to ask who actually read a revision of which draft now, the or that bad? Or either? Sorry, Vidi, did you want me to take over
Yes,
now?
can you run a poll? Can you run a poll for these questions?
Yeah, definitely. Okay, so let's focus on ORLADBAT. Who has read the ORLADBAT draft? Please raise your hand in the chill. Oh, actually, I've read it. Huh. Okay, we have 6 people in this session who have read the draft. That's not too bad. And now I think we were wondering if it's ready to be published. So I invite anyone who has comments on the draft right now to raise their hand. Alper, have you read the draft?
No, I haven't.
Okay, we are interested in comments from people who have read the draft. So
I haven't read, but can I make a quick comment?
no, thank you.
Thank you.
Okay, so I'm not hearing anybody with a strong opinion on this draft. Colin, did you want to say something?
Yeah, hi. I can't work Meet Echo on my phone. Colin Perkins, I read this a while ago because I mean it was discussed a few years back. From what I remember, it seemed to be in good shape and was very much going in the right direction. I guess it just needs a review to make sure everything is tidy and so on. But yeah, it seems like the sort of thing that the group should. Assuming the authors are interested in finishing it off, it seems like the sort of thing the group should reasonably be doing.
Very good. Thank you, Colin. So we as chairs, we were thinking of doing a research group last call, right? Last call for any comments, running it on the list after this IETF concludes, and see if we get any last minute, comments. And if we don't, we are interested in moving forward with publishing this document. So if nobody has any thoughts on it, I will take that as agreement, at least in a room. Okay. All right. If nobody else has anything to add right now, we are at the end of our agenda. We do have an open mic, and we have 24 minutes. So does anybody have a congestion control research topic that they would like to bring up right now? Alper, what's your congestion control research topic? Alper, did you want to ask a question to the room?
Sorry. I forgot to turn on my mic and video.
Okay.
Yeah. So let me introduce myself. I am Alper Kamil Demir from Adana Alparslan Alparslan Turkish and Science and Technology University in Turkey. We are working on applying named data networking into Internet of Things, IoT concept. We call it, actually it's not our calling. We call it named data networking of things. There's named data networking testbed. So the major challenge in named data networking, one of them, is interest flooding attack. So we published.
If I may interrupt you for a second, so is this congestion control, because it sounds more like it's a different research area?
No. I will make it connected to. So recently we introduced interest flooding attack methods, where we think that this method also can be applied to detect to prevent congestion in named data networking of things. even though it is interest flooding attack method. We haven't applied, we published our paper as an interest flooding attack method, but we think that it will also give some benefit in congestion control.
Okay, well, that sounds like a great idea. If you have a paper that is published, or if you want to share some early work, you are invited to send an email to the ICCRG mailing list to get some discussion and feedback.
Okay, I will
Right.
share. Thank you very much.
Yeah, for sure. You're welcome. All right. Do we have anyone else who wants to do open mic? Oh, I'm not seeing anybody. So I declare this ICCRG session concluded. Thank you, everybody, for the great participation.
Thank you, everyone.
Thanks, Vidi.